Hi everyone, this is Mr. Lee. In this video, we are going to look at gravitational forces for unique scenarios. Alright, let's begin. So, let's start off with a normal scenario, a normal planet. So I'm going to draw the planet like so, right? So this is my sketch of the planet. And I'm going to represent the center of the planet with a little dot there, right? Because it's important that we view planets as not a 3D object, but a point particle. And let's say, we'll just call this mass of the planet with a capital M. And let's say we have a person or an object right there on the surface of the planet. And so we can say that from here to here, let's call this lowercase r, or rp for radius of the planet. All right. Now, we know that for situations like this, when we're looking at two objects that's represented as a point, by the way, the reason why you're a point is you compared to the Earth, you look like a tiny little dot. We can use this formula here where we have G, capital M, so that's the mass of the planet, lowercase m, that's you. And we have R squared, or in this case, we could put that as RP. All right. And if we were to take a look at this formula, and if I were to say, all right, what if we shot you away from the Earth, right? Like, what if you jumped like super hard, and you pushed the Earth away? And so instead of having you on the radius of the planet, let's say you're out here, okay, and now you have a new radius. Let's do this new radius in green. Okay, so from here to here. So this is your, I don't know, your R prime. All right, so in this case here, all right, the idea is according to the gravitational force, because you're further away, right, and now we're looking at this relationship here, okay, between f of g and r, which is the inverse square relationship. The further away you are, the weaker the gravitational force. And the relationship is the inverse square. So if we were to draw a graph, I'm going to do this right here, where this right there is the radius of the planet. The further away you go from the radius of the planet, it has like this inverse line that looks like that. Okay. Now, what about this middle part? Ooh, so that's a question. What if you were to dig a tunnel and you were to go through the planet? What would that look like? What would happen to your weight? That's a cool question. So let's dive into that. All right, so I'm just going to do a resketch of this scenario here, but this time, instead of the Earth, I'm going to draw a tunnel. We're going to go back to the graph, so give yourself a little space for that. All right, so here we have the planet, okay, and we're going to draw a tunnel. Actually, that tunnel is too long. Let's draw a tunnel from the surface to the middle. All right, so that's exaggerated tunnel. All right, so let's say you dig, and you dig through the tunnel, and you get through. Let's see, small eraser right there. Right, that's your hole, and you go through the middle of the Earth, so that you're right there. All right, so this dot right here, that represents capital M. That's the Earth itself. But now look at this. You have a new radial distance away from the center of the Earth. So something unique happens. When you are not on the surface of the planet, okay, the idea is there's still a f of g acting on you. So I'll draw that in red here. Okay, the Earth is still pulling you to the middle of the planet, but it acts almost like a smaller planet itself. So that dotted line is the mass. So I'm going to draw it again here, right? So it's only this part of the planet that actually affects the pull. Anything beyond it, I'm going to shade this over here. This part right here that I'm about to shade in, okay? That part of the planet has nothing to do with pulling you towards the middle, okay? That part of the planet actually pulls you away from the middle, but it's minuscule compared to the inside of the Earth itself. So we only care about the radial part that's encapsulated within the radius between you and the center of the planet. Anything beyond that, so in this case the green part, does not matter. Okay, so it's almost as if we took a big planet and we kind of just shrunk it down to where we care about. All right, so in that case, right, so as you're going through the planet, what happens to your weight? So if we take a look at the situation, we can say the following. All right, so here's a couple of big ideas. The idea is that these planets have a uniform density. Ooh, uniform density. Now, we've seen this phrase before when it comes to ropes or strings, a uniform density rope or uniform density string. But the idea for a planet is that it's describing a ratio. So this is the Greek letter rho, R-H-O, and it describes the density of a planet here, okay, in this case. So it could represent different things, but for our situation, it's a planet. And the ratio is the mass of the planet versus the volume of the planet. So watch what I do here. I'm going to put a capital P here, so that represents the total mass of the planet over the total volume of the planet. And just so you know, because we're dealing with spheres, we're going to say this is 4/3 pi. And what I do here, I'm going to use a capital R, and that capital R represents the actual radius of the planet. So I'm gonna put that in here so we don't forget. Right there, let's do that in purple. So from here to here, this is capital R. And usually in physics and in math, whenever you're dealing with a constant, it's used with a capital letter. Okay, so capital M for the actual mass of the planet, and a capital R for the actual radius of the planet. So this is a ratio. Okay, now we can also use the same idea of a ratio for as you are going into the planet. Because as you are going into the planet, the mass of the planet is actually shrinking with the volume of the planet, because the ratio has to hold true. So here, I'm going to say, sometimes they use prime notation to show you that it's different. So in this case, I'm just going to use a lowercase m. So I'm going to try my best to make sure this looks like capital M, because that's the constant, right? That's the actual mass of the planet. And this is a lowercase m with the prime to show you that we're going into the planet. And so the idea here is, what's the variable, right? What's changing as you go into the planet? And the answer is the radius of the planet, Mr. Lee. So we're going to use a lowercase r. So if I were to go back to my drawing, that would be represented, let's do blue here, from here to here, this is your lowercase r. So your uppercase r is the actual constant, so that's the radius of the planet, and this lowercase r is wherever you are in respect to the center of the planet, okay, or the quote-unquote the new radius of the planet. All right, so we have here, this is, and the reason why I put all of this in a singular line is because it all is the same ratio, okay, and so it's a constant. So the idea is, let's say the mass of the planet is, I don't know, 1,000. Okay, and the volume of the planet is, I don't know, let's say 2,500. Okay, so this ratio would be 1/25, right? So that's the ratio. And so what this means is that if this is the ratio of the total mass of the planet, which is 1,000, versus the total volume of the planet, which is 2,500, it doesn't matter where you are in terms of the center of the planet, this ratio must hold true. So for example, if we are at a point where the mass of the planet is 10, then that means that the volume of the planet must be 25, because this ratio is the same as this ratio. So as we dig in further and further into the planet, the volume shrinks, but also the amount of mass that's pulling you in shrinks. All right, so with that idea, now we can actually figure out what happens as you go further into the planet. All right, so here we have f of g is equal to g big M, lowercase m, over r squared. All right, and the idea here is we now that we have this up here, this ratio, we're going to use that ratio to perform a substitution. All right, so let's define what that substitution is going to look like. So if we take a look at this formula here, we have two different m's, and the only m that's actually changing when we go from on the surface of the planet to inside the planet is this capital M right there, and that's where this ratio is going to come into play. All right, so whatever I highlight there, we're going to try to substitute the appropriate variable. So if we take a look at this crazy line above where there's three equal signs, okay, watch what I do. So I want to change this capital M into a new M, because once again, as a reminder, we're going into the planet, and as we go into the planet, the mass that is pulling in, it decreases. All right, and so when I say the mass that pulls us in decreases, the mass that I'm talking about is that M right there. So we're going to try to create a substitution where we have m prime p. All right, so I'm going to take this part of the formula that I'm about to circle, yeah, that part, and try to create our substitution there. All right, so if I have capital MP over 4/3 pi r, capital R cubed is equal to m prime p divided by 4/3 pi r cubed. And remember, this is just my notation of knowing that we're going into the planet, right? So we want to substitute in this m prime p into the formula, because this m, it used to represent the entire planet, but as we go into the planet, that m is changing. So if I rearrange everything, something really cool happens, right? This all, like, it looks kind of crazy, but a lot of things cancel out mathematically. So what I'm doing is this denominator here, okay, I'm putting that on the other side. So if I put that on the other side, we get pi r cubed. We get something that looks like this, where this parentheses used to be in the denominator. And so here we have 4/3 pi, and here we have 4/3 pi. Hey, you know what happens there? You guessed it. Algebraically, it cancels out. So this cancels out, this cancels out, and this cancels out with this, and so all that cancels out. So all that's left is actually the following. So as you go into the planet, okay, we are looking at MP, where that capital M is the actual mass of the planet, r cubed divided by capital R cubed. So in this case, so this is a function, right? So the idea of the function is that the mass of the planet is dependent on how far you are into the planet, or where you are according to the planet. And I'm going to put all my constants over here, and this r cubed is my variable. So this is my relationship. So if I plug this function into my formula, we get the following. And once again, try to make this a habit, but anytime there's a substitution, try to put that substitution into parentheses so you can see what is changing, all over r squared. Okay, so whatever this parentheses is, that came from this line here, and we can see, right, even more algebra happens, some more algebra magic. So here we have r cubed in the numerator, and here we have r squared in the denominator. Hey, and you know what happens when you clean that up? We get g mp versus regular m r all over r cubed, and this is the gravitational force, where r is your changing variable. Okay, so what this shows us is something really cool. The gravitational force, or how hard the planet pulls on you, is dependent on all of these constants and this one variable here. So the relationship is the following. Okay, it's a 1-to-1 ratio. It's a linear ratio. So I just want to point that out one more time, that anything that is not within this parentheses here, okay, so that is your changing variable. So anything that is not variable is considered to be a constant. So all of this is a constant. Okay, the mass of the planet is a constant, that capital R is a constant, that lowercase m, which represents the person going into the planet, that's a constant. So the only thing that's changing is the force of gravity and how far you are into the planet. And that is a linear relationship. All right, let's go back to our first graph. So what this shows us here is that when you go from the surface of the planet, okay, to the interior of the planet, it's a linear relationship. Oops, let me make that a little bit straighter. It's a linear relationship. Okay, so that's straight. So here we have versus here, which is cool. So here we have a linear line, and here we have a inverse square law. So let's just talk briefly about this point right here. So the question is, if you were to go to the very center of the planet, how heavy would you feel? And the answer is, you would feel weightless. Isn't that cool? Let's go over to my sketches to explain why. So if we look here, right, the closer we get into the surface of the planet, remember the force of gravity is the amount of force that the surrounding mass pulls you in. But if you are at the center of the planet, right, and so this is the rest of the actual planet, because you're not being pulled towards the center, because you're already at the center, there is no gravitational force that's pulling you to the center, because you're already at the center. Right? This kind of sounds redundant, but that's the reason why. At the center, your F of G is 0. You're weightless. You're just floating there in the middle of the planet. Whoa! All right, that's it. See you next time. Bye-bye.